Alright folks, we're working with non-right triangles again today. We're going to do the law of cosines, and then we'll review a little bit of law of sines, other triangles mixed together at the end here. So to start out, what I'd like you to do is try problems 1 through 5. You should be able to answer those with a little bit of knowledge from geometry. Okay, so pause the video and try 1 through 5. First one is just Pythagorean theorem to check. When we're talking about not using calculations, what I wanted you to look for here was just how we know angles and sides opposite of them relate to each other. So here, it appears to be an obtuse triangle, so this 11 is larger than our other two sides, and then of course when we square those, those are going to be the same. But from geometry, there was 3 relationships that you learned. If a squared plus b squared equals c squared, that was a right triangle, and that's the Pythagorean theorem itself. But if we took our a squared plus b squared and compared it to our c squared, where the c squared was larger, like this situation, okay, this side being larger went with an obtuse triangle. And similarly, if we had a squared plus b squared, compared it to that third side, and this third side, when we squared it, was smaller, then that was an acute triangle. Okay, so I was looking for something with talking about the type of triangle versus the numbers itself. Numbers itself came into play on part B, and there was a difference of 36. Then I gave you this little expression here, which happened to be very, very close to 36. Okay, it's very close to our difference. And when we talk about sine, we'll build into how that comes up with the law of cosines. So here, it says, calculate that with our original, and it ended up being 0. And that's because triangle 1 was a right triangle. So we shouldn't have a difference between the a squared plus b squared and the c squared because we're supposed to be equal. Okay, and that 0 came out because we know cosine of 90 from the unit circle, that x value is 0 there. Okay, but we want to use this to come up with a relationship between the 3 sides of triangle for any. We know from geometry that if we're dealing with a right triangle, we can say c squared is equal to a squared plus b squared. Okay, and those are interchangeable, the order. But there's a reason I put it this way, okay? From what we're talking about up here, this number was very close to our difference, but our difference was 36. And we want to think about whether that's a positive 36 or a negative 36. So I had some people in class kind of rearrange this a little bit to say, well, this is the same thing as saying the difference between those values is 0 for a right triangle. And then from this, it was very close to our difference, and this difference was represented with this equation. I could say c squared minus that is equivalent to the 2ab cosine. But it wasn't exactly equal, it was close to, because this was a negative, whereas the other version that we came up with was a difference of a positive. So to fix that, we just need to tack a negative on either side, and then it's easier to put it on this side since that's only one term, whereas this has really 3 pieces if we distribute that negative through. Okay, this is the built version of the law of cosines, which says I want this c squared by itself because I'm used to seeing Pythagorean theorem this way. But I want the stuff all kind of on the same side. And so what that looks like for us is c squared equals a squared plus b squared minus that 2ab. And a lot of times you'll see me write it with a times cosine c. You'll see why here in a minute. But I want to show you this is equivalent. So here, the difference between these two expressions is the squareds were moved over. So if I were to move both these squareds over, they would both get subtracted. And this negative distributes through where they both stay subtracted. Okay, so this is the traditional version you'll use. But I want to talk about pieces that are involved for this equation, just like we did with law of sines. So as a reminder, law of sines from last time looked something like this, and there's multiple versions of it. But we had a side and the angle across from it twice. In a triangle, we just had to have 2 pairs in order to solve, with one of those values being an x and the rest of them filled in. With the law of cosines, that's not the case. We have 3 lowercase letters, which means there are 3 sides involved, and we have 1 uppercase, which means 1 angle involved. But if we look at our matching up, there's not 2 pairs of sides with angles, there's only 1. And so that's the major difference between this and the law of sines, is when we set up our triangle, there's only going to be 1 pair, and just like with this one, in our 1 pair, there was going to be an x involved. For us, in our 1 pair, there's going to be an x involved in one of those 2 places. We have to know the other 2 sides. Okay, so let's look at some examples here. First up, when we read through a problem, we want to sketch a picture. Look out for words that would indicate this could be a right triangle, because that'll save you some time. In this one, it just says, find the measure of the smallest angle in a triangle with side lengths 4, 5, and 6. That's not a Pythagorean triple that we know, so we're drawing just a regular triangle, and those numbers on each side in whatever order you want them. And it wants us to find the smallest angle, so from geometry, that's across from the smallest side. And we're going to start picking on pairs. So that x matches up with that 4. And for this one, we can't find another pair in the picture, but we want to think about that. Okay, we know it's law of cosines today, but in general, they're going to be mixed together. So because there's no other angle given to us, there's no way for us to pair up. Okay, we can only solve for a third angle, not a second one, if we don't have one to begin with. So this is the law of cosines, and I'm going to have you just write the formula for this first one so that we can see all the different steps that goes into solving this equation. Okay, so remember, this pair is what goes here and here. It has nothing to do with C being the largest side anymore, because this is not a right triangle. So C is just the side across from the angle that you're working with. So across from the one we're working with is this 4. So that's going to be 4 squared. And then the other 2 sides go in for A and B in whatever order you want. So then same thing here, 2 comes down, and whatever order you want, those same 2 numbers. And we don't know the angle, so that's our x, or you can leave it C. Okay. From there, we have to watch order of operations. We've got exponents, we've got addition, subtraction, and multiplication. I can't type this whole thing into my calculator, because order of operations says I have to multiply before I add subtract. And because I don't know C, I can't multiply these together. So to avoid that, we're going to move the addition subtraction over to the other side so that those squareds are friends. So that looks like 4 squared minus 5 squared minus 6 squared. And then we're left with this negative 2 times 5 times 6 on this side. Okay. From this point, this is something that you can toss in your calculator, this side and this side. Okay, so that's our next step, is just simplify those. Okay, so from here, this is negative 45, and this is negative 60, times our cosine C. Now, the reason this whole time that I've been adding this extra times instead of just smushing them is for this step. A lot of times when we see this negative, many folks look at it like a minus, and that we need to add that over. But we're trying to get it away from this cosine, and so we have to focus on getting rid of that. So we're dividing by negative 60. Now, when we have cosine C, this can be a positive ratio or a negative one. In this case, it's a positive 0.75. And our last step is going to be using our inverse to solve. Okay, so inverse cosine today, 0.75. And it says to the nearest degree, so it's about 41 degrees. Okay. For this one, we don't have to worry about there being 2 possibilities, because cosine, remember, our restriction is anywhere from 0 to 180. So if there was an obtuse angle, our calculator would tell us from this ratio being negative. Okay. All right, number 7, it gives us a parallelogram. Okay, so as a reminder, we've got 2 pairs of parallel sides in a parallelogram. And it says we've got a 70-degree angle. So I'm going to put it down there. And side lengths of 10 inches and 15 inches. But with a parallelogram, opposite sides are parallel, they're also congruent. So I've got 10 inches here and 15 inches here. Okay, similarly, opposite angles are congruent, so I could put a 70 degrees there. And these missing two angles are also the same size. And from geometry, the consecutive interior angles are supplementary. So that's 110. Another way to think about that is we know that all four angles in a quadrilateral add up to 360. If you take off the 140, you're left with 220. And because those are the same size, you can split that in half for 110. Okay. So we've got all that information in there, and now we go to the question. It says, what is the length of its longer diagonal? So that tells us that the diagonals are not the same length. Okay, if you didn't draw your picture accurately, this is going to be more challenging to see. Okay, but the longer diagonal is actually going to connect the smaller angles to each other. So it'll be going this way. All right, now, with a parallelogram, there is no rule that says this diagonal bisects that angle. So those 70 degrees are actually not things that we can use. We're going to just focus on this triangle here, that we've got 10 inches, 15 inches, X, and this 110 that we found using the 70. From there, I've only got one pair because, again, I can't say that this is 35 degrees. Those do not have to be the same size. Okay, from here, we're looking at this equation again. And the thing outside is the thing we start with. So that's x squared. Then my other two sides. 2 times those sides again. And then cosine of the angle, and this time we know it. Now, solving for a side with law of cosines is a lot easier than solving for an angle because x is mostly by itself, which means all of this is fair game to go in our calculator. We couldn't do that before because this cosine c was in the way. Okay, but this one, we can type that whole thing in. So we'll do our 10 squared plus 15 squared. All the way through here. And you can just use times. You don't have to use parentheses there. Okay, we've got about 427.6. Doesn't matter what you round to here because we're not done. That is x squared. We can see that's way too large for this triangle. We still have to take the square root of it. So about 20.7 because it doesn't tell us what to round to. We just have to make sure we put that label on of inches. Okay. What I'm going to have you do now, since we've gone over one with the sides and one with the angles, is I want you to pause the video and try 8 and 9 for me, and then we'll go over it when you come back. Okay. So here I recommend just drawing a basic triangle and labeling your 3 spots, the laser telescope, the center of the throwing circle, and then the target, and then filling in the sides after that. Okay, so it tells you from telescope to the throwing circle is 30.10, says telescope to target is 50.02, and the angle between, this is the weird part, it says the telescope's path to the target, so telescope's path to the target, and to the center of the throwing circle, because they didn't repeat anything, we're assuming we're starting at the same point. So laser telescope to this throwing circle, that angle between those paths is 45. From there, it says find the length of the throw from the center to the target. Okay, so that's our x, and we can use law of cosines to solve. Okay, now number 9 here, the first one, okay, we want to use law of cosines to solve for. And it doesn't matter which side in general that you set by itself. So you could have started with 8 squared equals, 6 squared equals, or 5.3 squared equals to set up the rest. As long as you know which angle goes where, that's no problem. And you can check that by just looking at your triangle and making sure that the largest side is across from the largest angle. Okay, but what I want to talk about here is a way to switch to law of sines from last time. So law of sines, solving for an angle is more challenging than a side, but solving for an angle with law of sines still is less work than using law of cosines. It's not as many steps. The problem with law of sines is, remember, when you solve for an angle, there's always the possibility of the supplement. Okay, you have to take 180 minus that value and check to see if it works. So if you want to be able to switch to law of sines, what you have to do is find the largest angle first. Okay, when we think about this triangle, there's only one possibility for an obtuse angle. And the only one that's possible to be obtuse is the one across from the biggest side, the one across from the 8. So if we solve for that first, then we will get the obtuse angle if there is one. In this case, there wasn't one at all. But by doing that, if we switch to law of sines, the angle that comes out from our calculator, the acute angle, is going to be the only possibility because the obtuse was taken care of. Okay, so if you want to switch to law of sines, just make sure you solve for the biggest angle first. And then from there, okay, we're just doing the math on 2 of them. I always want you to subtract from 180 to find the third. If you were to find all 3 of these separately and round them to tenths, likely we would get something like 179.9 or 180.1 degrees with some rounding. Okay, so just subtract to find that third one. Okay, I'm always going to find biggest angle, second biggest angle, and then subtract to find the smallest one. Okay, if I have to find all 3. All right. Number 10 and 11 are more review from last time. Okay, I'm going to help you get started on number 10, but then I'll let you try it as well. It says we want to find the height of a White House using Trig and a clinometer app, which just measure angles. It says you can't find your distance all the way to the building because there are hedges blocking your path. So you're over here, and this is the White House, but there are hedges in the way where you can't literally get a tape measure and measure out the whole way. Okay? So instead, what they have going on here is you're going to measure angle using your phone app twice, and you're going to measure a distance just 10 feet apart. That's way more reasonable. Even if we could measure all this distance, just to measure off 10 feet, rather than, potentially hundreds of feet, okay? So with that in mind, we're given just this information to solve for the height of this White House. And right now, that's just not enough information to solve for it. Okay, so what I want you to think about here is what information from geometry you can fill in. When we see height, we know this is a right angle, perpendicular to the ground. Okay, but we also know a lot about angles in the triangles. So we can find a lot of the missing stuff just by knowing that the 3 angles in a triangle add up to 180. That's going to help us because as of right now, the only side length that I have is this piece right here. And if that's the only side piece I have, I can't find h yet. Because in order to find a side using law of sines, law of cosines, or SOHCAHTOA, I need to have at least one other side on the triangle. And right now, this h is not part of this little triangle here. Okay? So we've got to solve for some missing pieces first. With that in mind, I want you to pause the video and see what you can find out in terms of solving for h. Get as far as you possibly can and come back when you're stuck. Okay? Hopefully, you saw that this was 145 degrees based on these being supplementary. And then that would make this 2.5 degrees. And that we needed to find either this inside side or this outside side in order for us to use the right triangle that this h is part of. Okay? So I'm going to use this inside one just because the number 35 is nicer. And that one was a more obvious right triangle than the larger one, perhaps. So if I want to do that, I need to solve for this side using this obtuse triangle. I'm going to redraw it so you can see it more clearly here, but this is my x, this is my 10. Okay, this is my 2.5 degrees, And then I need across from this, which is your 32.5. So from here, law of sines looks like x over sine of 32.5, and then equals 10 over sine of 2.5. So then I just need to take 10 sine 32.5, enter or close your parentheses, then divide it by your sine 2.5 to get about 123.2. Okay, if you had done this with the outside, it would have been about 131.5 to check if you got that one. Okay, from there, we can use SOHCAHTOA, or law of sines again, to find the actual height that we need, because now I have two pairs to work with again. So if you're using SOHCAHTOA, that's opposite, and this is hypotenuse. It's literally sine. So sine 35 equals the h over the 123.2. Okay, or same thing would have applied with law of sines. I could say h over sine 35 equals 123.2 excuse me, 123.2 over sine 90. Okay, and this is equivalent because here all you do is multiply that over, here all you do is multiply that over, sine 90 is 1. Okay, so it doesn't matter if you want to use law of sines instead. And then similarly, if you had the 131.5, same process. Okay, this angle would have been your 32.5. For a final answer, of about 70.66. If you use the whole version here, I believe it rounds to 70.65 instead, meaning if you grab that whole value from your calculator because you have it, it just rounds a little bit differently, and I would take either. So I'm just going to call this about 70.7 feet. Okay. Number 11 is entirely review. You'll have to use law of sines, but I do want you to try this one on your own here. Okay, so pause the video, sketch that out, and you're going to find angle Z, angle Y, and Y, and it says all possible values, so that's a hint to check for something extra. And then you're going to find the area of the triangle or triangles, if there were two, when you're done. Okay, this one. When I say triangles, plural, it's because when you find a missing angle using the law of sines, which is what we were doing here, solving for this Z first, you have to check the angle that comes from your calculator and the supplement. Now in our case, if I check 168.3, that's not going to work because that's across from the 3, and that's an obtuse angle, which would mean it has to be across from the largest side, and it's not. But also, if you take 168 and 42, we're over 180 degrees, so that just does not work. So it's not possible for that one. Okay, so we get rid of that and just do the math to solve for the rest of them. Okay, once you have two angles, subtract to find the third. And then we can use that picking on pairs, the y with that, and I always use the original pair to go find that missing side. From last time, your formula, okay, 1/2 AB sine C. There were lots of different ways you could find this area. What's important is whatever angle you pick. So I picked this 42.5. You have to choose the two sides that are around it, the 3 and the 12. So if you wanted to choose this 128.5, you'd have to use the 3 and the 10. Okay, so all of these, if you round to one decimal place, will look the same, about 12.2 units squared. If you rounded to more than one decimal place, you may have slightly different numbers if you did different values. Okay, so be careful on that. Okay, just the two sides and the angle in between it in order to use that formula. Your homework has a lot of word problems where if you have to draw out pictures. Okay, remember there are possibilities where you're dealing with right triangles and you can use SOHCAHTOA. Look out for those. And then there's review of your inverse sine, cosine, tangent as well. Okay, so if you have any trouble setting up your word problems or with those review problems, please come see me.